Aloha, my name is Chong Ho Alex Yu. In this presentation I would like to talk about how modern physics challenges our ontology, epistemology, and views of mind. I am a philosopher, a psychologist, and a data scientist. I don't just wear multiple hats, I collect them. Which is why I now know just a little bit about many things. But I tell myself that's still better than being an expert in absolutely nothing. For much of the 20th century, serious philosophy was told to stay in its lane. Under the influence of positivism and later logical positivism, metaphysics was dismissed as idle speculation. Only what could be verified by observation or reduced to logical analysis counted as meaningful. Questions about the ultimate nature of reality, the status of mind, or the thing in itself were treated as leftovers from a pre-scientific age. Yet in an ironic twist, it is now physics itself, general relativity, quantum mechanics, and thermodynamics, that keeps dragging us back into metaphysics. When black holes behave like information storage devices, when spacetime looks like a hologram, and when erasing a single bit of data has a precise thermodynamic cost, it becomes very hard to say that philosophy is just speculation. Physics has become a prod for serious philosophical reflection about ontology, epistemology, and the nature of consciousness. One way to see this is to ask what, fundamentally, the universe is made of. 19th century physics gave a fairly straightforward answer: matter and fields in space and time. Today, that picture looks almost quaint. General relativity tells us that spacetime itself is dynamic. Mass-energy curves spacetime, and that curvature tells matter how to move. Quantum field theory says particles are excitations of underlying fields, and quantum gravity research suggests that spacetime geometry might emerge from more primitive data, especially patterns of entanglement. Black hole thermodynamics makes the point especially vivid. Bekenstein and Hawking showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. In information theoretic terms, the maximum number of bits that can be stored in a region is set not by how much space is inside, but by the surface area of its boundary in Planck units. The holographic principle pushes this to its philosophical limit. In some models, everything that happens in a three-dimensional volume can be fully encoded on a two-dimensional surface surrounding it, like a cosmic hard drive whose capacity scales with area. This is no longer a story about little billiard balls flying around in a pre-given stage. It is a story about reality as a web of information that can be represented in profoundly non-intuitive ways. From an ontological standpoint, it becomes tempting to say that matter, energy, and even spacetime are not the bedrock, but emergent renderings of a deeper informational structure. The universe not as a warehouse of stuff, but as a vast, self-updating database whose entries happen to appear to us as particles and fields. When ontology asks what there is, epistemology asks how and what we can know.
Who am I?
You are number 6.
What do you want?
Information.
Here too, physics has turned information from a mere metaphor into a central concept. Classical epistemology worried about justified true belief, certainty, and skepticism. Modern physics invites us to think in terms of information channels, noise, and limits on knowability. Shannon's information theory tells us how much information can be transmitted reliably over a noisy channel. Quantum mechanics adds a twist by telling us that there are fundamental limits to how much information we can obtain about certain properties simultaneously, as in the uncertainty principle, and that copying unknown quantum states perfectly is impossible, the no-cloning theorem. These are not just practical engineering constraints, they are principled boundaries set by the structure of the world. Black hole physics reinforces this. The information paradox forced physicists to ask whether quantum information is truly conserved. Much of the recent work in quantum gravity assumes that at the deepest level, the evolution of the universe is unitary. Information is never destroyed, only scrambled into forms that are effectively inaccessible. Landauer's principle then ties this information-centric epistemology back to thermodynamics. Landauer's principle states that any logically irreversible operation must be accompanied by the dissipation of a minimum amount of heat into the environment, thereby increasing the total entropy of the system and its surroundings. The simple act of forgetting, resetting a memory register to zero, has an unavoidable energetic cost. This makes information feel very concrete. It is not an airy abstraction floating above physics. It is welded to entropy and energy. Maxwell's demon is a thought experiment proposed by the Scottish physicist James Clerk Maxwell in 1867 to challenge the second law of thermodynamics. He imagined a tiny, intelligent being, the demon, guarding a trapdoor between two chambers of gas at the same temperature. By only allowing fast, hot molecules to move to one side and slow, cold molecules to the other, the demon could, in principle, create a hot side and a cold side without using any net energy, thereby decreasing the entropy, disorder, of the system. However, Maxwell's demon is defeated precisely because its information gathering and memory erasing operations have thermodynamic costs. The demon must observe each molecule's velocity and record this information in its memory. For the demon to operate continuously, its memory must be reset or cleared to record new particle data. What looks like a purely epistemic act, gaining and discarding knowledge, turns out to be a physical process with real energetic consequences. Epistemology and thermodynamics meet. Knowing and unknowing are not free. They are as constrained by the universe's bookkeeping as any chemical reaction. Nowhere is the tension between physics and philosophy more vivid than in the philosophy of mind. The hard problem of consciousness asks why any of this physical and informational machinery feels like something from the inside. Why is there a first-person perspective, what it is like, associated with brain processes, rather than just third-person behavior? Traditional materialism often sounds like a promissory note. Once we map every neural firing and correlate it with reportable experiences, the problem will dissolve. But if physics itself is now written in the language of information, we can try a different angle. Treat consciousness not as an inexplicable add-on, but as a special mode of information organization. Integrated Information Theory, IIT, for example, proposes that consciousness corresponds to the amount and structure of integrated information generated by a system. Instead of starting from neurons, it starts from phenomenology. Experiences are unified, structured, specific, and definite. Integrated information theory then asks what kind of physical, informational systems could have those properties. Roughly, a system is conscious to the extent that its causal powers cannot be decomposed into independent parts. That is, to the extent that it forms an informational whole that is more than the sum of its parts. The resulting measure, often labeled phi, is a kind of informational volume of the system's intrinsic cause-effect structure. This resonates strongly with modern physics. Just as quantum error-correcting codes store logical qubits in patterns of entanglement that cannot be localized to any single subsystem, a conscious brain might be seen as storing and processing experiential content in patterns of causal, informational integration that cannot be reduced to isolated neurons. On this view, the brain is not just a wet computer. It is a high-dimensional information network whose integrated structure has both an outside face, what physics measures, and an inside face, what it feels like. Consciousness becomes the subjective aspect of certain complex informational structures, much as spacetime geometry might be the geometric aspect of certain entanglement patterns. This does not magically solve the hard problem, but it reframes it. If the universe at bottom is informationally structured, and if certain informational structures have an intrinsic, experiential aspect, then consciousness is not an inexplicable spark in an otherwise dull material world. Instead, it is what happens when information becomes sufficiently integrated, self-relating, and dynamically rich. In a very loose metaphor, you might imagine the universe as an enormous, ongoing computation. Most of its subroutines are dark, blindly churning away. But some subroutines, brains, perhaps other systems, are complex enough that the computation folds back on itself, constructing a model of its own states. From the outside, we see neural activity and informational processing. From the inside, that self-modeling process just as experience. Putting these threads together, physics no longer leaves philosophy behind. It drags philosophy along and demands that it keeps up. Ontologically, we are pushed toward a view where information and structure, not little bits of stuff, sit at the base of the hierarchy. Epistemologically, we learn that knowledge and ignorance are not mere mental states but physically constrained processes with real thermodynamic footprints. In the philosophy of mind, we are invited to see consciousness not as a ghost in the machine, but as the intrinsic perspective of certain complex informational architectures. The old positivist hope, to expel metaphysics and talk only about observables, has been complicated by the fact that our best theories of observables now come packaged with deeply metaphysical questions about what the world is like in itself. If this is right, then philosophy and physics are not rival disciplines but partners in the same long project, trying to understand what kind of thing this universe is, what it allows us to know, and what it means to be a knower within it. I have sketched one way of reading contemporary physics as a friend, rather than an enemy, of serious metaphysics and a richer philosophy of mind. But the story is far from settled. The conversation between physics and philosophy is not over. In some sense, it has only just begun. The integration of science and philosophy also delivers a sobering message about our everyday intuitions. Common sense perception evolved to help us dodge predators and find food, not to penetrate the deep structure of reality. It tells us that objects are solid, that time flows uniformly, and that causes always precede effects in a simple, linear way. Physics tells a stranger story. Spacetime can curve, stretch, and even form horizons. Quantum systems can be entangled across vast distances. Information can be bounded by area rather than volume. Erasing a bit in a memory heats up the environment. Against this backdrop, it is risky for philosophers, or anyone, to dismiss ideas simply because they are counterintuitive, offend what seems obvious, or violates basic logics, while leaving out the constraints of modern science and mathematics. If reality is more like a hologram, a quantum code, or an information theoretic network than like a collection of little pebbles, then our common sense ontology is closer to a useful fable than a final map. Perhaps the right attitude, then, is intellectual humility, a willingness to let physics and information theory revise our deepest categories of substance, cause, mind, and world. I would warmly welcome comments, criticisms, and alternative perspectives, especially from those who interpret consciousness, information, or space-time in very different ways. If you found this video informative, please share, like, and subscribe. Thank you for watching. Mahalo.